final leg of this course. In some of the topics that we have seen so far, let's say in capillary statics, we found that there is a relationship between the various surface energies that are present in the problem and the contact angle, the equilibrium contact angle at the wall. This is the angle between the fluid interface and the solid. We call this the Young's angle. Now, we also looked at problems where the angle was assumed to be fixed, such as capillary rise in a tube, where we ignored the effect of contact angle varying with time. We've also looked at several problems where there is no contact angle at all. These are problems such as the Rayleigh plateau instability, problem related to thin films, Marangoni instabilities, and Rayleigh Taylor, Kelvin-Helmholtz instability, and so on. In many of these problems, there was no contact angle at all. We also saw situations where the contact angle at the wall, even in a static situation, need not be the Young's angle, and this was in the context of wetting on textured surfaces and rough surfaces. In such problems, we saw that the apparent contact angle is related to the Young's angle, but also related to the surface roughness parameters. So that's one example where we can actually have an angle at the wall which is different from the Young's angle, even though you're in a static situation. I will now show you a few cases where we can still, the droplet or the liquid can still be in a static situation, which means it's not in motion, and the angle can be different from the Young's angle. So what does this tell us is that it tells us that the angle, Young's angle, is not the only solution that is a viable solution for the problem. In some of these problems, a range of angles are possible solutions. So let's look at this from with two examples, and the primary reason of giving these two examples is to highlight two things. One, many of you must have experienced these examples in everyday life, and two, I want to highlight that even for a very simple problem, what you're going to see in a minute, even for these very simple problems, there are still many unanswered questions. So let's begin by looking at liquid in a tube. It's a plug in a tube. So the problem that I have in mind is a capillary tube, and of course, for the sake of drawing, I'll basically make it appear like a very large tube, but you should really imagine tubes whose diameters are very small. And we have a liquid plug in this tube. Right? So this is the liquid plug that we have here. And we also have gravity in this problem. Now, these kinds of many of you must have seen these kinds of plugs in tubes. Let's say when you're working with a garden hose. But of course, one has to keep in mind that in most of those problems, if you shake a little bit, the fluid would basically drain down. Often it will just drain down on its own, and this air pockets that you see in the thing in the garden hose is not a contact line dominated phenomena. But essentially, I want you to imagine that something similar can happen for very tiny capillary tubes. In fact, in these capillary tubes, the liquid can get trapped in these capillary tubes, and it's not that easy to get rid of these plugs. Chemists actually use this to actually transfer reagents from one place to another using these tiny capillary tubes, because you can control the amount of liquid that is going into the capillary tube. So what exactly happens in this? Now, if you see that this plug is stationary, let's look at the free body diagram on this. If you say that the plug, it's a long plug, but I'm only showing it as a thick plug. But you can imagine a very long plug where the height of this plug is much larger than the radius. Let's look at the forces on this plug. So this is liquid column in a capillary tube. So let's look at the forces on this plug. So at the very top, let's say the angle here is theta 1. So this is axisymmetric, therefore it's theta 1 here as well. This is theta 1. And the other side, let's say the angle here and here is theta 2. I'm showing it on the outside because I've shaded that region. This is theta 2, right? Now, if you ask what are the force balances on this problem, the force balances are as follows. You have weight of the plug, we'll call it as Fw, and this would be the density times the volume, pi r square times h multiplied by g. That's the weight. And surface tension force, Fs. There are two components to the surface tension force. The upper force would be surface tension gamma going all around the contact line, because it's a circle here. The contact line is a circle going all around the contact line. The upper one would be cosine of theta 1, and for the lower one it is gamma times 2 pi r times cosine of theta 2, but then the below one is negative, so I have a minus sign between the two. So if equilibrium is present, if the column is in equilibrium as in it is not moving, then I can say gamma times 2 pi r cosine of theta 1 minus cosine of theta 2 will be density times pi r square h times g, right? So this is what I have, and from this I basically can conclude that if I have the plug to be stationary, then theta 1 cannot be equal to theta 2, okay, which means that theta 1 is not equal to theta 2. That's the first thing, okay. In fact, we can also say one more thing. Cosine of theta 1 has to be greater than cosine of theta 2. That's one thing we know, and therefore theta 1 is less than theta 2. That's the first thing we know. So essentially the upper portion of the plug is actually making a smaller acute angle, and the lower portion of the meniscus that you see, that's what we call as theta 2, is slightly broader, right? The angle, but the angle is still acute, and so this is what we have here. So theta 1 is less than theta 2. So immediately we have a situation where we have at least two different angles, and these angles are both simultaneously, both the angles cannot be equal to the Young's angle, right? Now let's basically consider a situation where let's determine what is the maximum plug height that we can support. Maximum length of the plug that we can support this, we will call it as 2 pi gamma times 2 pi r times cosine of theta 1, we'll call it as min, minus cosine of theta 2 max. This will be rho times pi r square g into h max. So if I want to maximize the amount of liquid in this plug, then what I have to do is I have to make the difference between cosine of theta 1 and cosine of theta 2 larger. And one way to make this larger is I basically make the difference between theta 1 and theta 2 larger. So I make theta 1 as small as I can and theta 2 as large as I can. So now there is of course a limit to how large and how small you can go. So the idea is the following. We'll call theta 1 min we'll call it as uh, theta r, and or we'll just maybe use capital R, and theta 2 max, we'll call it as theta A. So the maximum height of the plug would be H max, and this quantity will simply be, I can cancel out a few things here. 1 R also gets cancelled. I simply have 2 gamma by rho R G times cosine of theta R minus cosine of theta A. So this theta R is called the static receding contact angle. Sorry, I'm making a few mistakes here. Contact angle, and theta A is the static advancing contact angle. So what do I mean by theta 1 min and theta 1 max? Is there a limit at all? Why can't I basically say theta 1 max goes all the way up to the maximum possible angle, which is 180 degrees or pi, and why can't I say theta 1 min goes all the way up to 0 degrees? Well, the reason for this is because one can carefully determine these parameters. These are determined experimentally. These are determined experimentally, and these parameters can be determined carefully using experiments for different combinations of liquids and solid surfaces. Of course, there are variations based on the nature of the solid surface. For example, whether the solid surface is smooth or rough and so on. These numbers can differ, but one cannot theoretically assume that the theta r will actually go to 0, or theta 2 max will go to 180 degrees. Now, now I've also used these words advancing and receding. Let me also, I haven't clarified that yet, but I'd like you to hold your thought when we look at the next problem, because that's where the ideas of advancing and receding become easier to understand. Okay, so let's basically hopefully I've given hopefully the main purpose of this simple problem, a capillary problem, is that to demonstrate that you can actually have angles which are different from the Young's angle. Okay, so this quantity, this difference that we have here, theta A minus theta R, this is referred to as the static contact angle hysteresis. So this is the difference between the maximum allowable angles for theta 2 and theta 1, or for the advancing and the receding regions. Okay, and I haven't still clarified why we call it advancing and receding, but you'll have to bear with me for a minute. So this is the hysteresis that we have in the problem. So a range of angles are indeed allowed, and we will also see why it's called hysteresis in a minute. But let's basically look at another problem. This is a problem of drop on an inclined plane. Well, let's do so. We can even consider the extreme limit of a vertical pane, vertical, let's say, window pane. as an example. Let's look at this case. Now, let's start with a simple case of a droplet that is basically sitting on a horizontal surface. It's making an angle which we can call as the Young's angle or the equilibrium angle. This is the Young's angle or the equilibrium angle. Now let's consider a situation where the plate is actually tilted. Now if the plate is tilted to this configuration, you may have all seen a droplet make it a little extreme. You may have all seen a droplet in this fashion. If you haven't seen it, then what I would suggest is go to the nearest glass window that you have, just sprinkle some water on it and see what happens to these water droplets. So what you will see is the larger droplets will tend to flow down. Okay. You'll also see that once if there is a water droplet which has made contact with a wet portion of the pane, if there is a certain wet portion of the pane, then the droplet will again flow down, meaning that you cannot. But then you will always have certain droplets which are basically just stick there on the surface. They don't move, and the front of the droplet, meaning the downward portion of the glass plate, this portion of the glass plate is dry. If this was wet, then the drop would again slide down, right? Now, there are now the angles become important. These are just an extreme case of this droplet. Maybe I'll just to put it to scale, I have. So this is an extreme case of the this is an example of the same thing that we are seeing here. We have two different angles, but now the droplet is not moving. So you see here, this angle here that we're trying to draw here, this angle is the receding. We'll call it theta small r, and the reason why I call it theta small r. This is theta small a. Now, the tendency of the droplet is to move downwards. So, essentially, what we have is this portion of the interface, which I'm trying to highlight with green. This is the advancing front. This is the advancing front. In other words, that is advancing into the dry region. And this one is the receding front. You can also make some more observations. You can also give some more labels. For example, there's this, sorry. You can also give some more labels. So I can identify a point right there at the contact line. I can call this the advancing contact line and the receding contact line. But hold on, somebody may say, well, we are saying that the droplet is not moving. So why are we saying that this is advancing and receding? The answer is that if you want to basically go from this horizontal case to the vertical case plate, there are several ways to look at it. If you go from a horizontal to vertical, then there is a much higher chance that the lower portion of the droplet, which I've called it as the advancing contact line, that will tend to move down. There is very little reason. In fact, there is actually no reason for this droplet to move up spontaneously unless there is an external agent which is driving it. For example, you could have wind blowing from the bottom or some other mechanism such as difference in surface tensions and so on. But if you ignore all those things, if you just consider pure surface tension, gravity and wetting phenomena, then there is a much higher chance that the bottom of the droplet will tend to move down and the upper region of the droplet will follow downwards. So that is the receding front. Now you can actually have this draw parallels between this problem and the previous problem, and again make the same kind of an argument. The same kind of argument which says that the gravitational force, a detailed theory for this problem is detailed force balance for this problem is not as straightforward as the capillary um, capillary tube problem, because the shape of the droplet is a priori unknown, and then it's not just dependent on the theta and theta r, it also depends on the surface tension, and you have to solve the Young Laplace equation to get the shape. But since we don't know the shape, we'll just make a simple scaling estimate. The idea is the following. The gravitational force in this case the weight, and this force scales like density times volume. Volume roughly scales like r cubed times g, where r is the some equivalent radius of the droplet. It could be an equivalent radius or some characteristic radius of the droplet, but we know it scales like r cube. That's what matters to us. And surface tension force or capillary force, we'll call it as Fs or Fc, surface tension force, and this quantity again scales like 2 pi r. That's basically assuming it to be the circumference of the contact line length to scale like r, 2 pi r times gamma. Again we have the same thing here. We have cosine of theta 1, and what we had earlier was theta r minus cosine of theta a. So that's what we have. So theta 1 is basically like theta r, and theta a is like theta 2, right? Now in this problem, what tends to happen is, here I'm showing a case where theta a is greater than 90. It's typically obtuse angle. Typically theta a is greater than 90 and theta r is less than 90. That's the most commonly observed situation, right? Again we have the same thing. If theta a is equal to theta r, or theta 1 is equal to theta 2 in the previous problem, the force balance is not satisfied. The force balance that we saw is not satisfied. And well, I should mention that for equilibrium, W should approximately be equal to Fs. I mean, of course, there are pre-factors that one has to put in if one wants to do a detailed calculation between the two. But if these angles are equal, then the surface tension force, the capillary force, goes to 0, and the force balance will not be satisfied, and in fact it means that drop will slide down. The drop or the plug in the previous problem will slide down. So it tells us that to support the drop or the column weight, we require a contact angle hysteresis. Right? You can only have this when you have a contact angle hysteresis. And in both these problems, if you actually do a force balance, you actually get well, you actually will get a relationship between surface tension and gravity as well. And there is a relationship between the size of droplet and the capillary length. So if the droplet becomes much larger than the capillary length, then obviously surface tension force cannot hold it together, and these you will actually have the droplet sliding down. So in other words, what tends to happen is this force balance itself will be fundamentally violated straight away. You have to take into account the inertia of the droplet, acceleration of the droplet, and so on, and motion of the droplet, and that several other forces come in, dissipation in the liquid and so on, all those things come in. But the bottom line is, if you want to support a droplet like this on a surface, then you require a contact angle hysteresis. Now let's look at the case of the lotus leaf. A lotus leaf or lotus effect this is basically commonly a common mistake that a lot of students make is they just think a lotus effect is just a lotus effect, or I can even say self-cleaning. A common mistake that several people make is to say that the lotus effect or the lotus self-cleaning effect is only because the surfaces are super hydrophobic. Correct? What is self-cleaning? The idea is the following. If you basically have if you have a surface like this, and this surface has a lot of dust and dirt on it, and if you take a droplet which rolls down the surface, what tends to happen is, as it rolls down, behind it, it basically cleans up the surface. Right behind it, it cleans up all the debris that is present. Okay, so this is basically referred to as the self-cleaning effect. The reason for this is the droplet basically, as it rolls down, it picks up all the dirt or the dust particles with it, and the surface becomes clean. This is how the lotus surface tends to be very clean. Now the reason it basically moves down is because there are two things that are happening. Contact angle is very large, static, or you'd say apparent contact angle is large, that is theta star is typically 150 degrees and above. The other thing is the hysteresis angle, that is theta A minus theta R is very small. So it's possible these days to make surfaces extreme hydrophobic surfaces where the hysteresis angle is as low as 5 degrees, or even maybe even smaller. So on those surfaces you hardly see any difference between these angles theta and theta r, and this immediately suggests that if you look at the force balance, cos of theta r minus cos of theta a will be practically very small. So capillary force is very small, and there is no other force to resist gravity, and therefore the drop will start moving, right? And once the droplet starts moving, the force balance itself will change. Now we have to write down Newton's laws, where we have acceleration terms will be equal to the gravitational force, and of course there could be other forces such as retarding forces such as viscosity and so on. But this force balance that we wrote down certainly will not work. I'm highlighting this force balance in the box. This won't work. So if you want self-cleaning surfaces, you not only require a large contact angle, you also require surfaces with a very small contact angle hysteresis. Okay, that's the first thing. Now what about surfaces like the rose petal, or sometimes referred to as, I think, just the petal effect? In rose petals, what tends to happen is apparent contact angle is large, but hysteresis is also large. So if you take a rose petal this is what tends to happen. You take let's say you take an idealized rose petal which is flat, then because the apparent contact angle is large, you have a droplet which is basically sitting on the surface, and this is the apparent contact angle. Theta star, and clearly it's large. But if you take the surface and invert it, I'm taking the extreme case of an invert. Okay, maybe we'll just do it step by step. Maybe we'll just do it for a case which is slant vertical plate. If you take a vertical case, then this petal can still have a very large angle, a very large hysteresis angle. This is theta r and this is theta a. It will not slide down. And you can again come back and look at the rose petal in the reverse way. If you take a rose petal which is hanging down, you have the same issue. You have a situation where the apparent contact angle theta star is very large and the droplet will just not fall down. So this is a case where the apparent contact angle is large and the hysteresis is also very large. And when that happens, then the droplets become too sticky to the surface. So this force here that we have written down, this Fs, or the capillary force, is almost like an adhesive force. It is what is actually holding the droplet onto the surface. And if this force were to weaken, which means that the angles were to become comparable to each other, then the droplet will slide down. Okay. Now, there is another way we can also analyze these problems, which is to look at how do we actually do a controlled measure of these hysteresis. One way to do this controlled measure of hysteresis is measuring hysteresis. One way to measure the hysteresis is the following. You take a flat, smooth surface, and on the smooth surface, you first place a droplet. Now, what tends to happen is if you once you have this tiny droplet, then you can inject a tiny needle into this. You have a tiny needle that you can control with a pump. And when you push fluid into this tiny needle, then this is what is likely to happen. What is likely to happen is that the droplet will basically spread a little bit. Right? And once this happens, then the angle becomes, well, maybe I should, let me redo that again. I made a small mistake there. What tends to happen is that the droplet will resist spreading, and the angle will keep increasing. And it will reach a threshold. So in each case, what is happening is that the angle, initially the angle was this, then the angle, I'm just showing the slopes there, then the angle has reached some critical value. So once it has reached that position, then the contact line position cannot be fixed anymore. So in all these cases, the contact line is initially fixed in space. When I say fixed in space, it remains at the same location. You are not actually in any way holding it there. So the natural processes will basically tend to stay there. So if I now can plot the angle as you do this experiment, as you keep pushing in more and more volume, or you could say volume or you could say time, both in volume and time are interchangeable here, because they are interchangeable because the assumption is that you're doing this experiment at a constant volume flow rate. Okay, so when time increases, the volume is also increasing, and you start off with some angle, you start off with some non-zero angle, and then the angle keeps increasing. It has reached some maximum value, and after that the droplet will start spreading. So from there onwards, I will show it on the thereafter, what you actually have is a droplet. This is the droplet that we have, and we have a tiny needle. We have a tiny needle inside the droplet. And once you've reached this critical angle, the droplet will just keep spreading with the same angle. So in other words, these um, these tangent lines that I'm going to try and draw, you should imagine that these tangent lines are basically parallel to each other. Okay. Now, so once you have reached this, then the angle remains constant for a large amount of volume. So we basically determined the maximum theoretically possible angle, and this upper limit, we'll call it as theta A. So the droplet front is literally advancing into the fluid, and we call it the advancing contact angle. Now let's basically repeat this experiment. We'll modify the experiment a little bit. What we will now do is we'll start sucking fluid out of this droplet. Instead of basically, in the previous example, we were pushing fluid. This way the piston is moving down. So these are experiments are done typically with a precision pump called the syringe pump, where we can control the flow rate. Now we are doing the other way around. So what kind of a droplet we have now? The situation that we have now is a droplet which is having an angle which is at theta A. So that's the theta A, right? Now if you start pulling the fluid out, if you start pulling this fluid out, where the motion of the piston is upwards now, then I'll show the droplet shapes in green now. The contact line position typically remains fixed initially there, and the before somebody may say, make a comment that my syringe is not penetrating inside, let me push the syringe a little bit in. So the angle basically keeps reducing, and it has now reached some lowest angle that is possible. So without the contact line moving, now I have the angle continuously keeps reducing, and then there's a point where below a certain angle, I have the contact line then move. So after this, the contact line then moves with the same angle, right? So what we are now seeing is that there is a cutoff that happens here, and this lower limit, we'll call it the receding. So there is a maximum difference that is there, which is delta theta, which is theta advancing minus theta receding, and this is referred to as the static contact angle hysteresis. Now one may say, well, where is static here? There is the droplet. We're talking about an experiment where the droplet is continuously moving. So why do we call it static? The reason we call it static is because the idea is that these experiments are done. If I want the static angle, these experiments have to be done in a quasi-static setting. A quasi-static setting means I basically am pushing in the fluid very, very slowly so that the fluid adjusts. The motion of the fluid does not really should not really influence the outcome. So the interface adjusts to the new volume that is present, and we will see what is the angle that the interface takes. So these experiments are typically done at a very low speed, where we are pushing in fluid at a very low flow rate, and we are typically we will keep imaging the droplet with the camera, and so the camera setup would be typically like this. So we have a stage on which there's typically a droplet or some fluid. We have a camera looking at the thing. This is a camera that is looking at the droplet, and we have a light source. This is a light source. So you have to make sure that the droplet, the camera, and the light are in a more or less in a straight line. And when light basically falls on the droplet, the light gets scattered. When it hits the droplet, it gets scattered through the droplet, but then rest of the light basically travels at a straight line and hits the camera. So in this particular image, and if you do an experiment like this, then what you actually see is the droplet will basically appear like this, this tends to be completely dark. So you have a dark droplet and rest of it tends to be bright, and from this we can use image extraction, image processing algorithms to get the shape of the interface and hence the contact angle. So hopefully I've given you some things to think about. The angle that you see in many situations need not be the Young's angle. It can be different from the Young's angle, and that's that could be anywhere between the theta r and theta a. That's the contact angle hysteresis that is allowed in the problem. And this hysteresis is the result why you see several many of our experiences in day-to-day life, such as, let's say, droplets basically sitting on a window pane and not flowing down. It's primarily because surfaces have a contact angle hysteresis. So engineers are constantly working, chemists, engineers, physicists are constantly working on how to basically tailor the surfaces for specific applications. In some cases, a hysteresis is undesirable. So if you want droplets to slide down a glass pane, let's say the windshield of a car, then hysteresis is not desirable. In some cases, for heat transfer applications, maybe having a droplet is not so bad. So it depends on the application, and whether one wants a droplet or not. Okay. Now the story doesn't end here. These are basically in the static situations. What about in the dynamic situations? Now we will, in the next couple of lectures, we'll also see situations where the angle can also change because of motion. So we have basically, in the static experiments, we have basically not brought in the velocity of the contact line, because even though in these quasi-static experiments the contact line motion moves, it is so slow that it does not really matter. But we can have situations where the angle is significantly influenced by the velocity of the contact line itself and what is the relationship between them. But you'll also see that this problem is actually easier said than done, because it's easier to pose than actually answer, because there are singularities in the problem. We'll see how classical approach to solving these problems, just with the classical boundary conditions that we've given in the course, they all will fail. So this may be a little counterintuitive, because on one hand, we tend to believe that all the boundary conditions that we use in fluid mechanics are robust and they work. This is largely true, but except in some special cases. One of the few cases where the conventional boundary condition of, let's say, a no-slip boundary condition may fail is in the contact line problems, and we will look at that in the next lecture. Thank you.